there is a branch of probability that deals with counting, and it's actually called counting theory, and it tells us things like the number of permutations or number of combinations we can find, and it is a useful concept. So that's what we're going to talk about today. Now, before we talk about permutations and combinations, let's talk about the rule of sum and the rule of product. So these aren't very surprising results, but let's see what these rules are. So first, the rule of sum. Rule of sum. And the rule of sum says that if you have two sets, A, B, such that A and B are disjoint, then already ran out of space, but say we had AB disjoint, then we see that the number of elements in the union of A and B is equal to the number of elements in A plus the number of elements in B. And this is precisely the rule of sum. And hopefully it's not too surprising, right? We have two disjoint sets, and we can see that the number of elements in here plus the number of elements in here is indeed the number of elements in their union, because they don't have common elements, so you can't double add these. In case they did have common elements, then you would have had to remove elements because you accidentally counted their intersection. But in this case, you don't have that, so the union is precisely the same as the sum of all the elements in, or the number of elements in each. That's the same as the number of elements in the union. Okay, so that is the rule of sum, and similar to that, we can talk about the rule of product. Rule of product. And the rule of product says that if you have two finite sets, A and B, then the number of elements in their Cartesian product, A cross B, is equal to the number of elements in A multiplied by the number of elements in B. So this is the rule of product. Okay, so there are times when these things are useful, and in fact, the rule of product can even we can use the rule of product to find the total number of permutations that can be found for a given set, but for a given finite set. But let's actually talk about the intuition behind permutations. So permutations are sort of an ordered sequence of the elements from a finite set, and that is ordered such that each element only occurs once. And how many of those permutations can you have? Well, let's actually take a look, and to motivate this, let's use an example where maybe you are at a party and you're playing spin the bottle. Let's say you're playing spin the bottle with your friends. You have, let's say, 15 people. 15 people, and there are 3 prizes. When you're playing spin the bottle. So now you want to find out how many different ways can these prizes be won by different people. How many different ways can that happen? So for example, how many different ways can the first prize, second place prize, and third place prize be won? And that's what you want to know, right? So we have 15 people. So first let's find out how many, say we had 15 prizes, not even just 3. If we had 15 prizes, then we could have had 15 ways for the first prize to be won, 14 ways for the second prize to be won, because remember, the same person can't win again, right? We don't have repetition. So each element only appears once in this sequence. So anyway, the same person can't win again. That's what we're enforcing. So then the third person has 13 ways, or 13 ways of winning, and then 12, and then so on until we finally reach 1, right? So this, I hope you can tell, is 15 factorial, because we would multiply 15 times 14 times 13 times 12 all the way down to 1 in order to find the number of permutations there exist. So this is 15 factorial, but this is the total number of permutations we found. So the total number of permutations is n factorial, right? Where n is the number of elements we have to deal with. So in our case, it was 15 factorial, but we're actually just looking for 3 people winning, or 3 people can win in our case. So you can't just have n factorial, but this is our case. We have 15 times 14 times 13, because there are 3 prizes and 15 ways for the first prize to be won, 14 ways for the second, and 13 ways for the third to be won. So this is the number of permutations we're concerned with. But if we take a look, this is very similar to n factorial, except it's missing the last 12 terms. So the last 12 terms, we can describe it as n minus r. And in fact, we're not multiplying that. So n minus r factorial, that can be divided from, that we can divide n factorial by to get rid of those lingering terms. So now we can see that to find r permutations, we need n minus r factorial things to be divided out from n factorial. Hopefully that's clear. So again, what we did was we had n factorial, we divided out n minus r factorial things, and we had, like 15 times 14 all the way down to 1. And here, this was, okay, so this was, this was, I believe, 12 times 11 times all the way down to 1. And we see all the stuff here cancels, with the stuff here, and all we're left with is 15 times 14 times 13, right? And 15 times 14 times 13, well, this is precisely what we wish to sort of find in the first place. We wanted 3 permutations, so we can find our permutations using this formula, n factorial divided by n minus r factorial. And hopefully it's clear why we used that based on the example we just did with the spin the bottle. Now, if we're looking at permutations, we can see that the number of permutations can be described in this way. But what about combinations? Well, with combinations, we don't really care about the sequence anymore. We don't care about what came first, what came second. We just care that, okay, they occurred together. These elements occurred together. So how many different permutations are there for each combination? Well, say we have R combination and R combination. Right? So let's say in our earlier example, how many ways can we have R combinations? So if we think about it, for each R permutations, there are 1 divided by R factorial combinations, right? And that follows from the fact that each combination has R factorial corresponding permutations, because R factorial is the number of ways you can arrange R things in R places, and that is precisely R factorial, and that is the number of permutations that exist. So if that doesn't make sense, you can think about it as you have, let's say, R slots, and you have R objects to put in those slots. And if you look at the permutations, we talked about the permutations you can put R objects in those R spots. That is going to be R factorial. But how many combinations are there? Well, you're only putting R objects in R spots, so there's exactly 1 combination. For 1 combination, there is R factorial corresponding permutations. Hopefully that should be clear. So now, if that's the case, to find R combinations, we can simply take n factorial over n minus r factorial, which is the number of permutations we found from the previous derivation, based on that example we did with the spin the bottle, and we found that this was sort of a formula that holds. And we discussed just now that we can divide this by R factorial to find the number of combinations corresponding to this many permutations, right? Because each combination has R factorial corresponding permutations, and we divide this whole thing by R factorial to find the number of R combinations. So in other words, the number of R combinations or we should say n choose r is equal to n factorial divided by n minus r factorial, and this is just from the permutation formula, divided by r factorial, which is the same as multiplying the denominator by r factorial. And this right here is the formula to find combinations. And sometimes you might see this written as n choose r, like that. And as for permutations, if you want to say the same kind of notational equivalent to this for permutations, it's often written as npr for permutations. But yeah, that's sort of the intuition behind permutations and combinations, and these are useful concepts. And again, counting theory, it occurs in many different places within this course, and we can probably find a lot of applications within computer science when we might want to use this. So it's good to have this in the back of your head, and sort of think of where this might be applied for different problems.